Hello learners, in the second lecture on soaps and detergent, we'll now discuss in detail about the synthetic detergents and of course different types of soaps. As discussed in the first lecture, the most important advantages of the synthetic detergents is better wetting and cleansing action and consumption by hard water because of higher solubility of their calcium and magnesium ions. Let us now discuss the principle of synthetic detergents in detail. Synthetic detergents, like soap, are compounds which have a tendency to dissolve in water and also in oils and other non-aqueous materials under certain conditions. Hence, most of them are a combination of hydrophilic groups on one end of the molecule with hydrophobic groups on the other. The hydrophilic groups make the compound soluble in water, whereas hydrophobic groups make the compound oil soluble. When detergent is added to water containing some non-aqueous material such as oils, the molecules of the surfactant orient themselves in such a manner that the hydrophilic groups project in water and hydrophobic group dissolves in the oil. As a result, interfacial tension between the water and oil is reduced and an emulsion is produced when such mixture is shaken. In many cases, the hydrophilic group is usually introduced synthetically to a hydrophobic material in order to get a compound which is soluble in water. For example, lauryl alcohol is most insoluble in water, but when it is sulfonated, the resulting product is soluble in water in all proportions. The alkali salt of it is a good detergent. It should be noted that the formation of detergent does not depend upon the solubility, but the ratio of the molecular weight of the hydrophobic to the hydrophilic part of the molecule. For example, detergent formed by the action of 10 molecules of ethylene oxide on lauryl alcohol is soluble in water and is a good detergent, but the same compound formed by the action of 5 molecules of ethylene oxide on lauryl alcohol is neither soluble in water and nor a good detergent. So, we discussed a number of topics like soaps, cleansing action of soaps, difference between soaps and detergents, then surface active substances and principles of synthetic detergents. Moving forward, let us now simply revise what are detergents. A detergent is a surfactant or a mixture of surfactants with cleansing properties when in dilute solution. A large variety of detergents like laundry and fabric softeners, all-purpose cleaners and combinations for soaking, rinsing or bleaching. Usually, they are sodium salts of long chain alkyl hydrogen sulfate or a long chain of benzene sulfonic acid. There are different types of detergents: cationic, anionic, non-ionic and amphoteric. Here I have given few examples. Now we'll take up these types of detergents one by one. Anionic detergents, their detergent properties is due to the anions in the solution. They are either long chain fatty alcohol sulfates or alkyl aryl sulfonates of sulfates and sulfonates. For example, alkyl benzene sulfonates, alkyl sulfate, alkyl phenol ethylene oxide sulfonate, alkyl glycerol ether sulfonate, methyl alkyl laurates. Anionic detergents were first prepared by the sulfonation of fatty alcohols. These alcohols were obtained from sperm oil which contains esters of higher fatty alcohols bound to acids. The sperm oil obtained from the body of the sperm whale was hydrolyzed by boiling with soda solution. The process is known as saponification, to obtain saturated as well as unsaturated fatty alcohols containing about 16 carbon atoms. High melting unsaturated acids were then used for the manufacture of detergents. Anionic detergents dissociate into long chain anion, which acts as the hydrophilic end, and the long carbon chain as the hydrophobic end. Coming to cationic detergents, it ionizes in aqueous solutions to yield a large cation and a small anion. This cation is responsible for its action and detergent property. They are amines and quaternary ammonium salts, mainly used as antimicrobial agents and preservatives. For example, amine acetates and alkyl trimethyl ammonium chloride. These are the examples of cationic detergents. Coming to non-ionic detergents, they are amphipathic and contain the conventional long chain hydrocarbon groups, but they differ from anionic and cationic surface active agents in that the hydrophilic group is not ionized but contains a relatively large uncharged non-ionic head group. This group is normally based on ethers or alcohols, for example, polyethylene oxide, glycerol, sorbitol and saccharides. Ethylene oxide condensates of alkyl phenols are well known truly non-ionic. Examples are chains of lower alkyl oxide combined with longer alkyl chains or alkyl phenols. In simple words, these are the detergents which does not contain any ion in their constitution and are non-ionic detergents. Examples of such a detergent is formed when stearic acid reacts with polyethylene glycol. The reaction is given. Liquid dishwashing detergents are non-ionic type. The tweens are one of the most widely used non-ionic surface active agents. These are fatty acid esters of anhydrosorbitols which have been made water soluble by ethoxylation of the free hydroxyl group with ethylene oxide. Coming to the last type, it is amphoteric detergents. Amphoteric surface active agents may be regarded as containing both an anionic and a cationic group in the same molecule. The anionic group is usually carboxylic acid, sulfonic acid or sulfate, while the cationic group is usually a quaternary nitrogen or an amino group. Example, sodium N-alkyl aminopropionate. The charge carried by the amphoteric surfactant can be determined by the pH of the solution. In alkaline medium, the surfactant will possess anionic properties, and in acidic medium it will exhibit cationic properties. Most amphoteric surfactants are completely compatible with cationic, non-ionic and anionic surfactants. The ability to mix cationic germicidal agent and amphoteric surfactants together, combining the properties low toxicity and mildness to skin, has resulted in shampoo formulations containing the better foaming amphoterics. Other uses for amphoterics include emulsifiers in toilet preparations and paints, textile softeners, germicides and hydrotropes. Sodium lauryl sarcosinate or dairy fat is a well-known example of amphoteric type of detergent, and it is used in the manufacture of toothpaste, shampoos, cosmetics and water emulsion paints. In a nutshell, anionic surfactants are compounds in which the detergency is realized in the anion. Cationic surfactants are compounds in which the detergency is in the cation. Non-ionic surfactants contain non-ionic constituents. Amphoteric surfactants include both acidic and basic group in the same molecule. Now let us talk of the soap making process. It involves a number of steps. saponification, then removal of glycerine formed in this, glycerin recovery and its purification, soap purification, drying, storage of soap flakes, finishing by using additives, cutting, forming, shaping, and then ultimately packaging when it comes into the market. Now there are raw materials which are used in soap making. First is the source of glyceride. The main source of slow lathering hard oils, tallow, lard, palm oil, whale oil, fish oil, greases, etc. Quick lathering hard oils include coconut oil, palm kernel oil, etc. Soft oils are soybean oil, cottonseed oil, inedible, olive oil, etc. Second is a rosin, a plant exudation product which mainly contains abiotic acid. The colorless variety of rosin is used in the manufacture of laundry soaps, and dark variety is used in the manufacture of colored soaps. Rosins make leather formation faster, increases the cleansing action of soap, and also in the softening of hard soaps. Rosin requirement of tallow soap is about 40 to 50%, while that of greases is only about 25%. Then caustic soda, which is available in the form of flakes, blocks and sticks, as well as in the solution of various strengths. In soap making, block form of NaOH is generally employed. NaCl is used for salting out of the soap. About 12.5 parts per 100 parts of oil to be saponified is used. Then we need the binding material. The cleansing capacity of the ordinary soap is improved by adding certain binding materials such as sodium silicate, soda ash, trisodium phosphate and borax. The binding materials improve soap texture, correct the alkalinity of the solution and prevent the formation of precipitates in hard water. Soda ash is available in various forms, but 58-degree variety is commonly used in soap making to the extent of 5 to 10%. Even borax is used as a binding material. Then we need the fillers. The bulk or the weight of the soap is increased by adding certain fillers such as talc, starch, Glauber salt, pearl ash, etc. without affecting the detergency of the soap. Then sometimes coloring material is also added. Organic dyes and inorganic pigments are generally used. Common coloring materials are methyl violet for violet shade, bismuth brown for brown, rhodamine or saframine for red, zinc oxide for white, chrome green for green, cadmium yellow or metanil yellow for yellow, ultramarine or methylene blue for blue, eosine for pink and vermilion for rose shade. Intermediate shades can be prepared by mixing these coloring materials. Then sometimes perfumes and perfume fixatives are also added in the formation of soap. The essential oils known as the perfumes impart fragrance to the soap. They may be natural or synthetic. For example, natural perfumes are sandalwood oil, lemongrass oil, clove oil, eucalyptus oil, lavender oil, cinnamon oil, etc. Examples of synthetic perfumes are jasmine, rose, lilac and musk. Certain perfume fixatives such as tolubalsam, gum benzoin, etc. are mixed with perfumes, as a result of which the essence or the perfume of the soap is not easily lost. This is the schematic diagram showing the manufacture of soap. This is the manufacture of soap by continuous process. Industrial preparation. The most common method for manufacturing soap is the saponification of fats and oils. This process includes heating fats and oils and then reacting with liquid alkali to make soap, glycerin and water. The neutralization of fatty acids using an alkali is the second major soap making technique. To procedure raw fatty acids and glycerin, fats and oils are typically hydrolyzed using high pressure steam. After distillation, the fatty acids are refined and neutralized by utilizing an alkali to generate soap and water. Let us discuss in short different types of soaps. We have toilet soaps. They contains no fillers except occasionally a little resin soap, and it has about 10% of moisture. The dry, neutral, neat soap from the kettle is pumped into a chilling roll, and the chippings are dried in rooms by steam. The dry chips containing 7 to 10% water is then dropped into a bladed mixer called amalgamator. Colors, perfumes, germicides and other ingredients are now added and thoroughly mixed. The mixture is next ground into the form of a paper-thin ribbons in polished granite roll mills. These ribbons are squeezed into powders in the form of thick threads, which are then extruded into bars. These bars are then cut into cakes, stamped and wrapped. The toilet soaps are easily soluble in water with profuse lathering. When we wash our hands, a lot of foam is formed, persistence of the soap fragrance, non-dyeability of the skin or fabric by the color of the soap, smooth, glossy appearance without any cracks. Then we have transparent soap that contain glycerin, which acts as a skin conditioner through moderation of the degreasing action of soap and maintains a thin film of moisture on the skin so as to keep it smooth and flexible. Transparent soaps are made by dissolving the soap in methylated spirit, filtering and distilling off the alcohol. Floating soaps contain fine air bubbles blown into it in the molten state. Soap powder is prepared by mixing soap with hydrated sodium carbonate so that the powder is dry. Now, shaving soaps contain a considerable amount of potassium soap with an excess of stearic acid. Medicated soaps have some phenolic antiseptics. Marine and industrial soaps are prepared from coconut and palm oils. Soap flakes can also be prepared by pouring the warm soap between two rolls. The small upper roll is heated by steam and the large lower roll is cooled by ice cold water. The soap sticks to the lower roll as thin film. The film is cut into the forms of ribbons which are scraped off and then dried. The dried ribbons are then cut into the form of flakes. In the manufacture of best quality toilet soap, purest, whitest and least odorous fats and oils are necessary to use. For this purpose, tallow, coconut oil, castor oil, etc. are used. For saponification, NaOH is used. This makes a hard and stable soap while KOH produces soft product. The quality of soap also depends upon the proportion of tallow used. If it is replaced by hardened oil, a greater amount of coconut oil is used together with some resin, the purpose of which is to make the finished soap sufficiently plastic for milling. Shaving soaps differ from the toilet soap in the process of saponification. In the manufacture of shaving soaps, saponification is carried out with potash as well as soda lye. It is also necessary to gain absolute neutrality in the finished product in order to prevent irritation as it is used on the skin. A creamy and lasting leather or foam is also important in case of shaving soaps. Rose toilet soap can be prepared by cold process with the ingredients coconut oil, soap oil of rose, geranium, oil of bergamot, tincture of musk and eosin. It is placed in crusher and agitated with some coconut oil to neutralize excess of alkali. Specified quantities of coloring matter and perfumes are then added. After thorough mixing, finally powdered fillers are added and crushing is continued till a uniform blending is ensured. Then it is allowed to settle in frames. We have carbolic acid soap also that can be prepared by taking coconut oil, tallow and carboxylic acid in a fixed proportion by weight. Soap stock is prepared by bleaching palm oil, best tallow and rosin. Blending of carbolic acid with molten soap is done in slightly alkaline medium because of the weakly acidic behavior of phenol. Carbolic acid should not be more than 5 to 10%, otherwise it may cause skin irritation. The soap should be properly dried also because of the hygroscopic nature of carbolic acid. Now we have liquid soap which are very commonly in use nowadays. It is generally prepared by coconut oil, caustic potash, borax, glycerin, sugar and water. The coconut oil is heated in a jacketed kettle at about 50 degrees centigrade and then agitated with potash lye. Considerable foaming indicates saponification. After saponification, sugar, borax and glycerin are added and the mixture is stirred with known quantity of water. The mixture is filtered, perfumes and coloring matter are added and then packed into labeled bottles. Liquid soaps have also been prepared by making use of mixture of KOH and NOH both. Then we have neem soap prepared by taking into account coconut oil and neem oil and Victoria blue and urinin blue. The caustic soda lye is added to water and then agitated with the oil mixture to get a thick paste of required consistency. Then perfumes, coloring matter and crutching is added and crutching is done until we get a creamy product, then which is allowed to settle, and then the set soap is cut into pieces and molded. Sulfur soaps can be prepared by blending soaps with elemental sulfur, coconut oil, soup and sublimed sulfur and crushed with perfumes and coloring matter to get a homogeneous thick paste. Again it is allowed to set in frames. These soaps are generally used for skin diseases. We have a variety of metal soaps. They are the metal salt of commercial stearic acid. The important metal soaps are zinc stearate, magnesium stearate, aluminium stearate and lithium stearate. They all have fatty or waxy and water repellent properties. They are generally available in powdered form. The term heavy metal soap is applied to soaps of a radical other than sodium or potassium. Heavy metal soaps differ from sodium, potassium and amine soaps in the manner that they are insoluble in water. The acidic radicals usually present are naphthalenic, oleic, palmitic, stearic or resin acids. Besides sodium and potassium soaps, there are some other soaps such as calcium soaps, magnesium soap, etc., which are formed as a result of interaction of calcium, aluminium, lead, etc. with fatty acid. The calcium, magnesium and aluminium soaps thus obtained are insoluble in water and so they are used as lubricants in paints. Calcium and magnesium soaps are lubricants and dryers in paint industry. Metallic soaps are used for a variety of purposes, for example, as dryers in paints, varnishes, lacquers and inks. Cobalt, lead and manganese soaps are widely used for these kind of purposes. They are used as flattening agents to remove gloss from paints and inks. Aluminium stearate is used when transparency is desired, and calcium, zinc and titanium soaps are used when transparency is not important. Copper and lead soaps are commonly used in anti-fouling paints. Aluminium, zinc and calcium stearates and palmitates have been used as thickening or suspension agents in non-aqueous medium. A specialized field is the thickening of petroleum oil to form greases. Calcium and zinc stearates have been used in synthetic plastic molding powders for improving internal lubrication and also to exert a plasticizing effect. They have been also used as mold lubricants. Now in the end we will discuss detergent binders and builders. These are the materials which can be used to bind cations, mainly calcium and magnesium, contained in wash solutions that result in water softening. Builders enhance the quality of water, thereby making the detergents work in more effective and efficient manner. The builder is usually a sodium phosphate of the type Na5P3O10 as a sequestering agent. The builders form chelated complexes with calcium and magnesium ions react with water, forming alkaline solutions. The detergency of the detergent is increased by adding certain builders. The builders are most exclusively complex phosphates. These are more than water softeners which are sequester the water hardening ions. They prevent the redeposition of fabrics of the soil from the wash water. Detergent builders soften water by holding free water ions such as magnesium and calcium. This prevents these particles to react with other ingredients of the detergent which could have caused them to work less efficiently or precipitate from the soap solution or the formation of the soap scum. In this manner, builders also help in extending the life of a washing machine. Soil molecules are sometimes bound to the cloth surface by calcium ion bridging. It helps in the removal of hardness from the environment and therefore help in the removal of stains. Sometimes more than one detergent builder is used in a product to develop a builder system with more effective cleaning performance. So learners, we have in this lecture discussed in detail the action of soap and detergent, the requirements in the preparation of soap and for the effective performance of soaps as well as detergents. Thank you.